Welcome back to Applied AI Engineer. So far Atlas has answered short questions. Today it learns to handle long documents, runbooks, reports, transcripts that are too big or too costly to stuff into a single call. We'll count tokens for real, set a budget, chunk a document, and compare 3 summarization strategies. We'll see exactly when prompt caching pays off, and we'll put a real dollar figure on the cost of context. By the end, Atlas can summarize a file of any length, picking its strategy automatically. Last episode we made Atlas reliable, structured outputs with pydantic schemas, tool calling, and a retry when the JSO came back malformed. Atlas now returns clean, validated objects. But the moment you point it at real work, the inputs get long, an entire report instead of a one-line question. And long context has two hard limits. It's finite, because every model has a fixed window, and it's expensive, because you pay per token. This episode is about respecting both. Here's the mental model. Every request has a fixed token budget, the context window. Into it goes your system prompt, your document, the question, and the room the model needs for its answer. The document is usually the biggest, most expensive piece. If a document is too large, it simply overflows, the call fails, or you truncate and lose information. So the first discipline of long context is simple: count the tokens before you send, and if it won't fit or costs too much, chunk it and summarize. You can't budget what you can't measure, so we start by counting tokens. Tokens are both the unit a context window is measured in and the unit you are billed in. Let's get an exact, offline, deterministic count. A token is roughly 3 to 4 characters of English, the model's atomic unit, smaller than a word. Both the context window and your invoice are denominated in tokens, so counting them is non-negotiable. We'll use TikTok. It's fast, runs offline, and gives an exact count. It's OpenAI's tokenizer, so for Claude it's a close estimate, perfect for budgeting. When you need the exact Claude number, the Anthropic SDK's count tokens method gives it, at the cost of one API round trip. The whole idea fits in 3 lines. We grab the CL100K _ base encoding, encode the text into a list of token IDs, and take its length. That's the token count. We load our sample document, a quarterly engineering report for Atlas, and print its characters, its rough word count, and its true token count. Watch the ratio between characters and tokens. It's the rule of thumb you'll carry everywhere. Real numbers from a real run. 6,000 characters, about 970 words, and 1,230 tokens, almost exactly 5 characters per token for this prose. That word-to-token ratio of roughly 4 to 5 is the back-of-envelope figure to remember. Tokens run a bit higher than words. Now that we can measure, we can decide whether a document fits and what a call will cost. Before we chunk, let's be honest about why this matters. You pay for input tokens and output tokens both. If you stuff the same reference document into every call, you rebill that document every single time, a quietly enormous waste. Modern windows are huge, hundreds of thousands of tokens, but large is not the same as free. Cost scales linearly with tokens, and so does latency. A bloated prompt is slower and pricier on every request. That's the bill we're about to learn to control. Sometimes the document is bigger than the budget, or simply too expensive to send whole. The answer is chunking. Split it into pieces that each fit comfortably, with a little overlap so nothing falls through the cracks. 2 rules make chunking work. First, split by tokens, not characters, because the window is measured in tokens, a character-based split can still overflow. Second, leave headroom, the chunk plus the system prompt plus the question plus the answer must all fit. We also overlap neighboring chunks by a few tokens, so a sentence straddling a seam survives in at least one piece. The trade-off is real. Smaller chunks mean more calls and more cost, so you tune the size to the task. Here's the splitter, working entirely in token space. We encode the whole document once into token IDs. Then we slide a window of max tokens across that list, decoding each slice back into text. The key detail is the step. We advance by max tokens minus the overlap, so consecutive chunks share a few tokens at the boundary. Encode, slide, decode, that's a robust chunker in 9 lines, and it can never produce a chunk bigger than the budget. Running it, our 1200 token report splits into 4 chunks, 3 full 400 token windows and a smaller remainder. Notice each chunk is exactly token bounded, and the start of chunk 1 overlaps the tail of chunk 0, that's the overlap doing its job. We now have pieces that each fit comfortably. The question becomes, how do we turn 4 chunks back into one coherent summary? There are 3 classic patterns for summarizing across chunks, and a good engineer knows when to reach for each. Let's lay them out, then put real dollar figures on the trade-off. Stuffing is the simplest. Put the whole document in one prompt and ask for a summary. It's the cheapest and highest quality when it fits. MapReduce summarize each chunk independently, the map step, then summarize those summaries together, the reduce step, it scales to any length and parallelizes. Refine walks the chunks in order, carrying a running summary forward and updating it with each new chunk. It preserves narrative flow but is sequential. Short document, stuff it. Huge document, MapReduce. Order really matters, refine. Here's the difference in one picture. MapReduce, on top, fans the chunks out. Each is summarized on its own, in parallel, and a final reduce step folds the partial summaries into one. It's fast, but because each chunk is summarized in isolation, it can miss a connection that spans 2 chunks. Refine, below, is a chain. It summarizes the first chunk, then feeds that running summary plus the next chunk back in, again and again. It preserves order and flow, but it's strictly sequential, so it's slower. Speed versus continuity, that's the trade. Let's make the trade-off concrete in dollars. These are Anthropic's published list prices, per million tokens, input then output. Haiku is the cheapest, Sonnet our workhorse, Opus the premium. The cost function is just arithmetic, input tokens times the input price, plus output tokens times the output price, both per million. No magic. Now we apply it to the same document summarized 3 different ways. Here's why the patterns cost differently. Stuffing is a single call, the document in, one summary out. MapReduce pays a per chunk overhead on the map step plus a reduce call, and it generates a summary per chunk. Refine resends its growing running summary on every step, so its input total creeps up. The shape of the bill follows the shape of the algorithm. Let's run it on our real report and read the table. And there's the real cost of each strategy on our 1200 token report at Sonnet prices. Stuffing is 1 call and 0.6 of a cent, by far the cheapest. MapReduce runs 5 calls and costs nearly 3 times as much, because every chunk pays its own overhead and produces its own summary. Refine sits in between. The lesson is blunt: if a document fits, stuff it, only chunk when you must. The cleverer strategy is the more expensive one, so reach for it deliberately, not by reflex. There's one more lever, and on the right workload it's the biggest one, prompt caching. When the same large prefix shows up on call after call, you shouldn't have to pay full price for it every time. Here's how caching works. On the first call, the model processes your stable prefix, system instructions plus the reference document, and the provider stores that processed form. That first call is a cache miss, billed at a small premium to write the cache. Every later call that begins with the exact same prefix is a cache hit, and the prefix is charged at a deep discount, often a tenth of the price. The rule that makes it work: put stable content first, the changing question last. Let's model the savings. Without caching, every question resends and rebuilds the full prefix. That's the simple multiply. With caching, the first call writes the cache at 1.25 times the input price, and each later call reads the same prefix at a tenth of the price. We hold the changing question constant and just vary how the prefix is built. To turn this on with the SDK, you mark the prefix with a cache control flag. The comment in the file shows exactly where. 10 different questions against the same 1200 token reference. Without caching, you pay the prefix 10 times over. With caching, you pay it once at a small premium, then 9 times at a tenth of the cost, and the input bill drops by 77%. That's the caching pattern in a nutshell. A fixed reference plus many varying questions. The one caveat: caching only helps when the prefix repeats. If every request is unique, there's nothing to reuse, and you skip it. A quick provider note, as always. The tokenizer we used, TikToke, is literally OpenAI's, so its counts are exact for OpenAI models and a close estimate for Claude. Caching differs in the details. OpenAI applies it automatically when it detects a repeated prefix, while Claude makes it explicit through a cache control marker you control. But the engineering discipline is identical across providers: count before you call, put the stable content first and the question last, and choose your summarization strategy by length. None of that is vendor specific. Time to fold everything into Atlas. The deliverable is a summarizer that takes any file, measures it, and picks its strategy automatically: stuff if it fits the budget, chunk and MapReduce if it doesn't. The heart of the summarizer is the plan function, and notice it makes no model call at all. It's pure measurement. It counts the document's tokens and compares against a budget. Under budget, the strategy is stuff. Over budget, it chunks and switches to MapReduce. We also reuse Atlas's provider adapter from episode 1, so the actual model calls go through the same one-line swappable chat function. Deciding before you spend is the whole discipline of this episode in one function. And here's the execution. If the plan says stuff, it's a single chat call over the whole text. If it says MapReduce, we summarize each chunk into a partial, that's the map, collect those partials, and make one final call that combines them, the reduce. Because everything routes through the chat adapter, swapping providers is still a one-line change. Atlas can now summarize a document of any size without you ever choosing the strategy by hand. Running the summarizer on our report, Atlas measures 1230 tokens against a budget of 1200, finds it just over, and automatically selects MapReduce across 4 chunks, no human in the loop deciding. Had the document been a little shorter, it would have stuffed it in one cheap call. This is the deliverable working. The strategy is data-driven, chosen from the measured length every time. And here's a genuine summary of the report, captured from a real model call. it's faithful, it picks up the pipeline Atlas became, the adoption and latence numbers, the move to token budgeting and the 3 summarization patterns, the win from prompt caching, and the pivot to retrieval next quarter. That last line is our cue. We've squeezed long context about as far as it goes, and the smarter move is to stop sending whole documents at all. Let's take stock of what Atlas gained. A deterministic token counter, so we measure before we ever call. A token-bounded chunker with overlap for documents that don't fit. A real dollar comparison of the 3 summarization strategies, so the trade-off is in money, not vibes. A caching cost model showing 77% of the input bill on a repeating prefix. And a summarizer that picks its strategy from the measured length. Atlas now handles documents of any size, deliberately and cheaply. Quick recap. Count tokens first, because the window is finite and every token is on the bill. Chunk by tokens with a little overlap when a document won't fit. Stuff if it fits, MapReduce to scale, refine when order matters, and put a dollar figure on the choice. Cache stable prefixes, but only when they truly repeat. Notice the theme of the whole episode, stuffing entire documents is expensive and clumsy. Next episode begins the RAG module with embeddings and semantic search, turning meaning into vectors so we retrieve only the few passages that matter, instead of sending everything. That's both cheaper and more accurate. See you there.